Hello everyone. Today we are going to talk about the asynchronous computing platform that we have built at Meta and how we have revised it over time to support more than a trillion workloads per day. I am Sayak Kundu, a software engineer at the serverless computing team over at Meta, and I'll be joined by my colleague Artem. Artem, off to you.
Thanks, Sayak. Hey everyone, my name is Artem. I'm a software engineer at Meta, also in serverless computing team. Thanks for joining our talk and let's get started. First of all, let's quickly recap on what asynchronous computing is. When we refer to asynchronous computing, we usually mean the process of moving certain workloads from critical path of your application to the background. Let me give you an example. When user sends a request to your backend, they usually expect a response back quite fast. And there are certain operations that are important in order to create this response. At the same time, there are many other operations that are also important and have to be done, but do not require immediate response back to user. These operations we usually refer to as asynchronous computation. Good examples of them could be sending some notifications, recalculating some caches in the background, and many others. Let's quickly look at the main benefits that asynchronous computations can give us as engineers who own these systems. First of all, it's scalability and reliability. The fact that part of the workloads are outside of the critical path and can be run in the background gives us way more flexibility in handling different failure scenarios and scaling different parts of the system separately. The second two are efficiency and developer productivity. Again, the fact that workloads are buffered and executed in the background gives us a way to apply different efficiency techniques to get some wins from this situation. Good examples of them could be some window type of aggregation, batching, or even just the fact that we can delay certain workloads by arbitrary time and save some peak capacity that our service is consuming. All these techniques and many other details of why asynchronous computations are important and how you can use them have already been covered by our colleague Carla in her talk in 2020. Highly recommend this talk, it's really great. You can find the link in the description. In this talk, we are going to focus more on the how aspect. So how the system works, how we built the platform, and how we evolved it over time. First of all, we are going to cover standard building blocks of any asynchronous computing platform. Then we are going to go through our journey since 2020 when the talk was taking place. We will tell you about the major re-architecture that we went through and the main benefits that we got out of there. In the end, we are going to explore the new opportunities that this re-architecture opened for us and the ways how you can use them in your system to get some efficiency wins, same way as we did. With this, I will hand it over to Sai.
Thank you, Artem. Now let us look at the main components which any asynchronous computing system is made up of. They can be divided into three layers. The ingestion and storage layer, which is the first one, which is the layer that the customer interfaces with. It is responsible for taking the workloads from the customer and ingesting it within the platform. It also has a storage component, which is responsible for buffering up the items for them to be executed eventually. Then we have the transport and routing layer, which is responsible for picking the items from or the workloads from the buffer and sending them off for computation eventually. And the last one is the computation layer where the items actually get executed during the runtime. Now let us take a look at how the system was back in 2020. Our platform's ingestion and storage layer comprised of the submitter, which is a service that the customer would interface with. They would push their workloads into the platform via the submitter. The submitter in turn would take this and persist this into Fox, which comprised our storage. What Fox is, we'll go into later. The transport and routing layer comprised of a component called dispatcher, which was responsible for taking the workloads from Fox and pushing them for computation. Now let us take a look at Fox. Fox is an abbreviation for Facebook Ordered Queuing Service. It's a distributed priority queue which we have homegrown in Meta and is used extensively. There are two good blog posts that we have in our engineering blog which describes how Fox works. For this talk, we'll go over the main features of Fox. Being a priority queue, it has an enqueue operation which the customer can call in order to push their payload into storage. Along with the payload, they also specify a deliver after timestamp after to indicate when the item will become available. For the DQ operation, when the customer calls it, then along with the item that's available for DQ, they also get a lease. Over here, the lease is configured to be that of 30 seconds. If the customer is able to process the item before 30 seconds or the lease time expires, then they would send Fox back an acknowledgement and the item would be cleared off from Fox because Fox treats the DQ operation as successful. However, if the customer is not able to process this or requires some retry or something else, then they would send back a NAC or negative acknowledgement, and Fox would treat the DQ operation as unsuccessful and make the item available again. The same also happens if the customer is not able to respond with any ACK or NAC within the lease expiration time and the lease expires, then the item becomes automatically available again because the Fox infers it as a lease expiration. So with those details in place, we can see that the transport and routing layer comprising of dispatcher was responsible for pulling the item from Fox, maintaining the lease and sending them for compute. If the compute is successful before the lease times out, it would ACK it. If it's unsuccessful or there's a timeout, then they would either NAC or the lease would expire and the item would become available once again. With these, I'd hand it over to Artem. Artem, off to you.
Thanks, Sayak. Now let's quickly take a look at the new challenges that we started to see with the system moving forward. One has already been described by Carla in her previous talk, and it is related to overall complexity of the system. What we started to see over time is that dispatcher is becoming the central component for many, many features. A lot of logic is added there, and over time it started becoming bigger and bigger and taking more responsibility. At the same time, it was heavily coupled with other parts of the system. So it was interacting with folks, managing leads, doing all the handling of errors and the protocol there. At the same time, it was responsible for allowing many generic features like concurrency limiting, rate limiting, enforcing quotas. And at the same time, it was also scheduling the workloads to compute and balancing the load. So this component became quite big and it became tough to scale the team operationally in order to support it. This is the first problem. And the second problem is that over time, we started to see more and more customers coming with increased need of running their asynchronous function from data which is already stored somewhere, but not in our queue. For example, in a stream or in a data warehouse or even just in a database. So, for example, the data is already written there and the customers want to run their function for every update that is written in the database. So all this was already possible in the old system, but required customers to write their custom solution for manually copying data from the original source to our system through the submitter. So basically, they always had to implement some lightweight logic of reading data from source and submitting it to our queue. This was introducing extra load for each and every customer who wanted to use this. And moreover, it was introducing a major inefficiency because essentially data had to be copied the second time in our storage just to be executed on the platform. Keeping in mind that not all types of storages fit well into the queue. For example, it might be hard and expensive to copy some high traffic stream into the queue or some data warehouse tables into the queue or any other type of database that you might imagine. It might introduce significant inefficiencies on the way. So to recap, two main challenges with the old architecture that we had. First, high coupling between components, which was causing increasing operational load and become harder to scale the team operationally and work on the same code base. And the second one is that we don't have a first-class support for external sources, which is causing repetitive work on the customer side and major inefficiency in processing their data. Let's try to see how we address these issues. So first, and the very obvious thing to do in this situation is try to break down system in a smaller components and abstract them such in a way that they have very clear responsibility and very clear contract between each other. So that's what we tried to do. First of all, we tried to abstract transport and compute layer from actual source and ingestion, where the data is stored. In order to do that, we also decided to revisit some of the fundamental design choices that we did in the previous system. So I'm talking about switching from pull mode of operating to push mode. So originally, what dispatcher was doing is pulling data from the queue. Just because the only storage abstraction is queue, we really didn't have any other option. And now, as we decided to be more flexible and build a generic abstraction around source, we decided to take a look. What if we apply push there? Let's quickly take a look at the old problems that we experienced with the pull mode. First of all, it's complex integration. If we want to build something, some adapter on top of every storage that we want to support, then each of them will need to implement the queue interface. So they will need to manage dequeues, acts, next, and the concept of lease, state of the item. This all is quite heavy. Although it could be generalized, it would still have to be put on every single data source that we want to support. At the same time, if we are just using the simple Thrift RPC, then the workflow becomes way simpler. What we do is each data source is wrapped with a lightweight Tailor component, which is sending RPCs to a unified compute runtime and synchronously waiting for response back. The second problem that we saw with the pull mode is related to spikes in latency due to transient error. Because of the concept of lease, when there is some crash or some part of the transport or compute layer is getting down, then we didn't have any other option rather than wait for lease to expire and item to be requeued. Because lease timeout is usually configured to some high number of seconds, it would heavily depend on the function running time that we want to execute. It usually caused quite significant spikes in latency. For some data sources, such as stream, that don't have a good random access story, it might even cause different items to be blocked together with this one that was experiencing lease timeout. On the other hand, if we are using the pull mode, then if we configure the network properly and RPCs are configured properly, then we get response almost immediately if something goes wrong and we lost a connection or there is some other type of issue on the way, and we can retry this item right away. And the last issue is load balancing. When we are running in a multi-region environment where different data centers are pulling data from the single queue, it's quite hard to control the speed at which each region is pulling the data. And it's quite hard to make them utilized equally. At the same time, if we are pushing data from the central place, it becomes way easier for us to control the relative load in each region and make sure that they're utilized uniformly. These are the advantages of the push mode against pull mode that we used before. Of course, it also comes with some downsides. The biggest downside of it is it's essentially an RPC. So we have to hold the open connections on the server in order to keep the response there. At the same time, we also have to allocate resources on the server side for these connections. And overall, RPCs are not a very good fit for long-running workloads. So if we're talking about like tens of minutes or even hours of running time, to do this at scale, RPC is not the best choice. And the second thing is that using the push mode requires us to put extra flow control logic on the source side in order to protect downstream from overloading. Because many different sources would be now independently pushing data to a single compute runtime, they might easily overload it. So it requires a little bit of special handling. Keeping in mind that for our platform, the distribution of running time is such that most of the workloads finish within seconds. These two were not major downsides for us. That's why we decided to proceed with the push mode. And the new architecture that we came up with looks the following. So first of all, there is a unified scheduling and compute runtime, which is interfaced by a Thrift service called Scheduler, which is responsible for scheduling any type of workloads in this particular compute runtime. It is also offering all the standard features that our platform provides to customers that are agnostic of the data source. At the same time, around each data source, we have built a small wrapper called Tailor, which is abstracting all the details of how this particular data source is storing the data and how we need to read it, and then doing Thrift RPCs to scheduling there in order to send workload to execution. With this, I will hand it over to Sai.
Thank you, Artem. So with those changes in place, we saw that in our final architecture, we were getting a couple of wins. The improved end-to-end latency and the more effective load distribution are consequences of the migration from pull to push-based architecture. Apart from that, we are also integrating to different data sources directly, and there's no duplication of data. That brings out a good efficiency, as well as all the data sources are supported as first class citizens on our new architecture. With these things in place, we saw that a lot of customers are coming to us with different data sources. Majority of them were use cases where the customer had queues or streams as their primary data source. This put us in a place where we could compare the learnings or the observations between the two. So let's look into those. So since we were using queues for a while, the main advantage that we saw in queues was flexibility around retrying. This was because we could maintain the lease on individual items and act them or nag them back depending upon whether the execution succeeded or failed. And this would make them automatically available for retries later without affecting any of the other items within the queue. This random access and the ability to retry was the main flexibility. However, this came at a cost. The cost was that of maintaining the lease and also the secondary index, which would allow us this ordering. Some of these problems automatically get addressed with streams, which we will look at in the subsequent slide. If we compare this with streams, we see that we lose out on some of the benefits and flexibility, like granular retries out of the box or random access to messages. But where it really shined was very fast access to sequential data. However, in our system, we had to provide the capability of retrying because we were already providing at least once delivery guarantee. To understand the problems around retries on streams, we need to also understand how we are reading the stream. Let's take the next few slides to deep dive into that. We are reading the stream in chunks of data and we are maintaining something called a checkpoint. The checkpoint demarcates till what point down the stream you have read. You progress the checkpoint as you are reading chunks and sending them for execution. Once the execution of a particular chunk completes, you progress the checkpoint onto the next chunk. However, if one particular single item within the entire chunk fails, then you can't progress the checkpoint further because that item needs to be retried. And what this leads to is something called a clogged stream, because even though you're holding the checkpoint for the retry to complete, the traffic on the other side of the checkpoint keeps on building and items keep accumulating. This had to be mitigated somehow. How we solved that was by using something called a delay service or a timer service. We will not look into the implementation of this one because it is explained in more details on our blog post. But what essentially this provided was a secondary service onto which we could offload the items to be retried, and eventually they would be retried by this particular service at some later configured point of time. And this also frees up the mainstream and we can keep on progressing the checkpoint further without clogging it. So with these things in place, let's look at the final architecture. In the final architecture, on the left hand side, you see the different data sources. There's the customer who is manually pushing in workloads into Fox through the submitter. There's also stream and data warehouse. And there are these tailors, which are adapters, which are operating on these different data sources to take the workloads and push it down to the scheduler. The stream tailor, as I already explained, also takes aid of a delay service to process retries. The scheduler is responsible for exposing a source agnostic generic API which would take in the workload, and it is responsible for maintaining source agnostic functionalities like flow control or concurrency, and it would push the items to computation and help them get executed. So with this final architecture, let me hand it over to Artem, who would go through the learnings.
Thanks, Sayak. As we are reaching closer to end of the talk, let's see what are the learnings that we can get out of it and how you can apply these learnings to get same efficiency wins as we got in your system. Let's go through that. Before we start, I just want to make a disclaimer that we tried to keep this talk quite high level. At the same time, we have a separate blog post which has way more technical details that you can use as reference. So if you are interested in more hardcore details, then please go to the blog post. You will find them there. Let's go through learnings. First, and the very obvious one, is that there is no universal recipe for all use cases when we talk about scale. So if you run things at scale, you always have to make trade-offs, you have to combine different solutions, you have to evaluate different options, you have to accept their pros and cons, and there is no perfect solution that would just fit all your use cases. So you have to be reasonable. The second point is stream plus synchronous RPCs. This is the most effective solution for a high volume of short running workloads. If you need to run a very high volume of very lightweight functions, then using stream as a backend and synchronous RPC as a way to execute them is the most efficient solution that would give you the highest throughput at the lowest cost. On the other hand, if you need flexibility, granular retries, and long function execution time, or any other per message granularity features, they always come with the cost of using queue or stateful service. So I have to be clear that this is just a fundamental problem of having extra indexes on top of this data, because you can't offer ordering without ordering secondary index. So you have to pay for the features that you want to use. The good news is that you are not really needed to strictly choose between both of them, and you can combine them and try to get best from both worlds. So if majority of your workloads fit into stream, you can use the stream all the way and build a separate solution on the side that will take care about delaying certain items for arbitrary time and then requeuing them back for execution. It can either use queue under the hood or any other technology. So that's it, what we had about learnings. Thanks a lot for joining us today and listening our talk. Hope you enjoyed it. See you in the Q&A section. Thank you.